Welcome to signal processing for millimeter wave communication 5G and G. So far we have covered the channel model extensively and some of the time varying nature and how we have solved the time varying as well as the static one. The static one is straightforward, the channel is modeled as a FIR filter, right? And the time varying part was more of a time series modeling. So, like autoregressive model, moving average or ARMA, and predominantly we have said that it can be the autoregressive model that takes the precedence. So, today we will be covering the channel estimation part for the 6 gigahertz and equalizers. So, we are still not in the millimeter wave, to be very frank, but this is required as a fundamental because the same concept will be propagated to the millimeter wave as well. So, the concept to be covered here are the equalizer concept, channel estimation concept, but this is a very general concept, nothing to do with millimeter wave or any 6 gigahertz. Now, let us do some signal processing applications using such kind of channel model. So, we know what is channel model at the end of the day, right? Now, what will I do with that? So, what should be my application or what should be my signal processing activities that will be involved in the transmitter side or in the receiver side? That needs to be known, because that is the core of the problem here, right. So, let us proceed here. So, which means that I started with a single antenna case. So, I have a single antenna and then finally, we will move to the multiple antenna and we will see what needs to be done, and then we will slowly move to the millimeter wave context. Okay. Now, this whole thing whatever I will be talking about are equally applicable for normal sub 6 gigahertz or any millimeter wave things. So, this is independent of that. Now, this is few of the applications that we have that we are going to highlight here. And once this is done, we will be moving to millimeter wave channel models. We have already discussed little bit, but now we will be going deep into that later on. So, some of the applications here. So, now we have understood that the channel between the antenna to antenna is actually an FIR filter. So, if it is an FIR filter, I can always have some sort of a transfer function. In fact, I should not say this FIR filter is a time invariant. In fact, it can be time variant, because if there is a Doppler, then it really becomes time variant. Now, let us not worry about the Doppler part again, that we can handle it separately. So, let us assume it is a static environment. The channel is a pure a filter, which is an LTI filter, linear time invariant filter. Let us say the transfer function is something like h of z. H of z. Let us take for h of z, we can have let us say I have L number of taps in this case. These are all digital taps, mind it. This is not analog. I think we have explained in details. What is digital tap? It means that when I sample the actual RF or analog taps, this is what I am getting it at the output of the ADC as per the sampling. So, if I change my sampling rate at ADC, I will see different number of taps, right. So, this tap is the output of the ADC tap. So, I am getting L number of taps. So, L tap channel is an L tap channel, right. Now, when I say L tap channel, I think you have well understood that all these channels do not simply take into account the antenna to antenna behavior. It starts from DAC, ends at ADC. So, when I say antenna to antenna, it inherently inherently it also takes into account the effect of all the DAC, filters plus modulator and demodulators, impairments, everything, all the effects whatever is present into the whole chain apart from the digital side, everything is your HZ. Okay, it is not just antenna to antenna, but I may draw it like that just for a simplification. Now, here as I am dealing with HZ, obviously I will always take into account the digital data, right? I am not going into any analog. So, everything is digital for me because this is where the signal processing is. So, everything is digital for me. Okay. So, all the analog, RF, everything is now inside this H0 to HL. So, everything is just within it. So, now what will be my data model? So, it is as if like I am giving SN to a filter, it is a filter, right, it is an FIR filter, and the output is a YN. So, what is the output? Just a convolution, right. So, I can say my YN will be H0 into SN, it is a convolution, it is a LTI system, it is a convolution, plus H1 plus dot 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 HL minus 1 and S of N minus L minus 1. Right. So, it's like a delay lines, right, like a FIR filter. So, this is what my system of this is my system of linear equations kind of I can think of. This is one equation that I can think of. Now, this is not a signal processing part. This is just the output representation. So, what are the signal processing that I need to do? Because that is the intention of this particular talk, that what are the signal processing that I can do based on the channel model, right. Now, let us put effort on that. Now, look at this equation, Yn is equal to so and so. Now, what is the intention of this equation? What is the intention of this transceiver? The intention is that I will be sending Sn, I will be receiving Yn. Now, from Yn I want to recover what I transmitted, this Sn. From which equation? From this equation. Okay. Now, this is a very typical signal processing application. Now, if it is a normal digital signal processing, this is done. But for us, the task is different. For us, the task is that at the receiver, you do not know what has been sent, right. Say for example, in fact, there is a slight more things will be there. So, I will be having a noise also. Okay. Let us assume that this noise is independent of my data system, and that is kind of a, you can assume it to be a additive white Gaussian noise. So, you can model it as an additive white Gaussian noise. Why? Because this noise is more of a thermal noise, right. If it is a thermal noise, usually thermal noise are mostly like a Gaussian noise, and it should be white in the sense that it can be present everywhere in the spectrum. So, it is a white, and this is naturally it is an additive in this case, and it is independent also. Most of the time it can be independent, like independent of with what? Independent with SN, independent with channel, those kind of things. But there may be some correlations depending on how the systems dynamics and complexity happens. But in our case, in our simple examples that we are taking, we are assuming that this noise is a completely additive white, and it is a Gaussian noise for us. And this noise component is very important for us, because this noise makes the whole Yn completely, the way we extract the data, the way we view the whole system completely different. This noise is so important for us. Now, this is what my data model, complete data, whatever you are seeing, this is my data model along with the noise. Of course, the noise has to be there. Now, what is my job? So, in a simple sense, I can think of this is some sort of a equivalent model of like this. So, you have an Hz here, okay. You are giving an Sn which is unknown to you currently. This can be your noise. This I am just trying to model that system of linear equation. So, as if like I am getting this. So, the same thing I am just modeling in a different way. So, you have a filter called Hz, where one side is your Sn, and then later on there is a additive component of the noise added, and then you get a data. Now, what is the job? Job is to get back your Sn from the Yn, and there are two more things that is hidden here. One is that this Vn is not known to you, okay, because you never know what the noise is, right. and this is a white noise. So that means at every time to time your noise samples can be different. So even if you estimate a noise, next time the noise can be different. So there is no point in even estimating the noise. So noise is unknown to you. So that means it's like a garbage. It is like a garbage bin or a kind of a dust bin, where dust is basically your Vn, and within it some gold part called Sn sitting there, and your job is to extract that gold from that dust bin. So that's all the job is, right? So this is the signal processing part from the communication aspect. So this extra part, this noise makes the whole thing different. Now here 2 points that come into picture. First of all, when I try to know what the Sn is, what about your channel? Is it known to me? Okay, number 1 point. If not known to me, how do I know the channel? Because what are you doing? You are sitting at the receiver. If you sit at the receiver, you really don't know what is the front end system, right? It is virtually impossible. So you don't know Sn definitely. At the same time, you really don't know your channel is, right? You don't know what how many reflectors, scatterer. At the same time, you don't even know from the transmitter side what are the power amplifier characteristic, what are the DAC characteristic. Nothing you will know it, right? No impairment, no information available to you. So the question is that the channel itself is not known to Yash. Okay, so when you are at the receiver, you don't know the channel. So now if you don't know the channel, there are too many unknowns, right? You don't know channel, you don't know Vn. Now you are saying you don't know Sn. Now out of all these unknown, I want to extract Sn. Is it possible? Well, that's a tougher job. So we solve one by one. The way the communication system works is that it is solved one by one. So first is that there is no point in knowing Vn, because at every point your Vn is different. But channel something that we can do, right? Because we have already learned the channel has a coherence time. So what does it mean? It means the channel don't change so significantly for a long period of time. Depends on Doppler, and we have well defined it. What can be the Doppler? It's in the order of 1 by 4 ds, right? So if the ds is small or ds is almost negligible, your channel is like for a long time it can be constant. So the time of observations, like the compared to my ADC speed I am talking at the receiver. So if I sample at say 100 megahertz, which is 0.01 microsecond, if that kind of system I am talking of, or even a 1 megahertz bandwidth system where my ADC sampling rate is 1 microsecond, channel hardly changes. So it is okay to assume channel is constant for wide number of cycles or quite long cycles. But the point here that comes into picture is that even if it remains constant, you have to know. You don't know. It remains constant, fine, but how do you know what the value is? So the first task that every system encounters is the channel estimation, because you have to first know the channel, and that technique will be known as a channel estimation. Though this topics is a detection estimation topics, I will not get into that, but I may show you some of the data model by which you can do that. The exact techniques can be just mentioned there. Some of the cost function probably I will explain it in this concept, because the same thing will be used in the millimeter wave as well. When you go to the millimeter wave, we will talk about the same language, like what is channel estimation, what is signal detection, all these things should be talked about there as well. So before I get into the channel estimation, so there are two tasks here. So one task is that I have to get into the channel estimation, but before that I have to know one more thing: noise. Noise, as I said, you don't know noise, right? Because at every sample your noise can be different, not like your channel. Channel at sample to sample, they don't vary, provided the Doppler is manageable. Even if the Doppler is high, at least for how high it could be, I mean, what is the maximum speed that that on earth you can travel, right? Even if you talk about say bullet train, it won't like a speed of light, right? It will never be. So when it is not like that kind of range, so you can assume that the bandwidth that you are dealing with, it can well handle that channel coherence time. That means the coherence time is much longer than your ADC sampling rate. So that's our key assumption here. Okay, so before I do anything, channel estimation, anything like that, I need to first know what is the noise part. But then unfortunately, noise changes at every sample to sample. It's a white noise, right? White noise meaning at every frequency it is present, and at every time that channel can, the noise value can change it. So it is virtually impossible to estimate, unlike your channel, it is virtually impossible to estimate a channel, a noise. In that case, the remedy would be to estimate the statistical parameter of it, because if you look at the kind of equation that we deal with, we always deal with statistical phenomena, right? Because in our case, H0 to HL minus 1, the taps, it's a statistical quantity. Then data Sn minus 1 can also be thought of a statistical quantity for us at the receiver level, because I don't know what has been transmitted, right? See, if I don't know something what is transmitted, I can assume it to be a statistical quantity as well. Similarly, the noise, and we are already assuming this is a Gaussian noise, or its distribution itself is like a statistical quantity. So for us, everything is statistical. So under that scenario, we have to think in a statistical language, right? So that means I don't know the noise, well, no problem. May I know its statistics, because that's important for my activities moving forward. So instead of estimating the noise, I want to know its statistics. I want to know its statistics. What is the meaning of statistics? PDF can be a statistics. If I know PDF, I am done. Now we have already assumed that noise is a Gaussian for most of the communication system. The kind of communication system we are dealing with, we safely can assume noise, thermal noise is a Gaussian noise. So which means that for a Gaussian noise, what I need? I need the mean and variance. That's the only two quantity I need to define a Gaussian PDF. Well, so which means that for this noise, if it is a Gaussian, I just mean its mean. I just need the mean and its variance. That's all. These two quantity, I need it, right? Question comes, then how do I know the mean and variance, right? Okay. Now third point, once I know my noise statistics, once I know my channel values, then only I can think of detecting my data, right? So this would be my third priority for us. But first, I have to know the first 1 and 2. After that, 3 can be done. Now the question comes, how do I know the mean and variance? Is it such a big task? Usually for noise statistics to know, this is one of the easiest tasks in a communication system, right? And there are many estimation techniques for noise. I am not getting into that, but trust me, that's one of the easiest technique. For example, say I am not doing any transmission, say I am just transmitting a 0. So what does it mean? The only thing that I will be receiving is the noise, right? In this equation, look at this equation, that red marked equations here. See, if I don't transmit anything, that's kind of a null time, right? That means I am not transmitting anything. For example, suppose you are speaking on a mobile, it appears that you don't speak all the time, right? The whole 24 hours it won't be speaking. You may be speaking for a while. After that, your mobile can be just sitting idle. There may be some data transaction going on, but usually it can be idle, right? So when that kind of scenario happens, when null time, I would say that there is no data transmission. So what the receiver can do at that time, maximum, it can just, if it wants, it can keep on sampling the data at the receiver. What will it receive? It will receive only noise, nothing else it will receive, right? Because there is no data, there is no channel. So it will receive only noise. So it takes a large amount of noise sample. Okay, so if it takes a 1000 noise sample, pure noise sample it will get in that case, right? If there is no data, then what it can do? It can extract all the statistics from the large data. What it can do? It can estimate the mean. How do you estimate a mean? For a large data, you can just take an average, simple method, or you can do some sort of a squaring and then take an average. So you can get a variance, you can get, so these are the different techniques of estimating the spectrum of the noise. I am not getting into that. So my point here is that these two terms are easiest quantities to be available to the system. Okay, so that means these things can be given. Second thing that is important for us is that given the second number one, given this point number 2, how do I get into the channel estimation part? Now again, this is an estimation topic, I am not getting into that, but I want to create a framework where you can think of a channel estimation, you can think of a data detection, both possible in the same framework. So let us think of that framework first. Okay, so to create that framework, as it is a single antenna system I am dealing with currently, and it's a channel with multiple taps. So let us assume, just for the time being, that I know the channel somehow. Okay, I know the channel. Once I create the framework, then you can create some mathematical manipulation and do some channel estimation framework. So because this number 1 and number 3, the framework remains the same. So let us assume that I know the channel, just for the time being you assume it. Okay, if that is the case, I can create some sort of a data model. Now we know what is yn, right? So let us say I know yn. May I know yn plus 1? Of course, if I know y, because that's an observation, right? I know yn, that means nth point observation. This is my n plus 1 point observation. So like that, I can take a lot of such observation. So let's say I take, n number of observation. Straightforward. So you have the ADC. This is my nth sample, this is my n plus 1 sample, this is my n sample, this is n plus 2 sample, and so on, so forth. I just take the observation point and I keep it in my memory. So now let us say I stack it. What is meant by stack? Stack meaning I just put them together. Okay, I just put it in one. It's kind of, you can think of a row. Mathematically, I can say this is kind of a column, not a row, column in a matrix form. So I stack it. Let's call that as a vector. This is a DSP. This is what the signal processing in the communication. So what can I think of? What can I think of here? Go back here. What is the data model here? H0 Sn, H1 Sn minus 1, and so on and so forth. This is what the data model. Now for your simplicity, okay, let's go into here. So for your simplicity, let me write the equation, then it might be easier for you to understand here. So the first one, the y1, what was the y1? Y1 was H0 Sn plus H1 Sn minus 1 and HL minus 1 this is the case, correct. For the second one, what is that? You just put as per what you are observing here, right. So this is H0, this will be n plus 1, right, plus this will be S, n will be there, right, and accordingly it will be adjusted, right. So whatever here, it will be plus 1 here. Okay. So what about the last one? Last one will be S of n plus n minus 1, right, plus H1 of one level will be down plus n minus 2, and so on and so forth, right. This is how, and there will be up to the, you can adjust it, what with the indexing here, plus I will assume this is a vector noise, because the noise is like a V1, V2 and so on. So I just stack it together and make it like a vector. So what will be the, so if this is the equation, how can I represent it? So I can say this will be some sort of a y bar What will be the case here? I can think of some sort of a Toeplitz matrix in this case. So, can I build some sort of a Toeplitz matrix in this particular case? Okay, we can do that. Definitely, we can create a Toeplitz matrix in this equation. So, I can just think of it H L minus 1, then it will be going like a H1, H0, lot of 0 will be there, and from here it starts from Sn minus of L minus 1, and then it will be Sn minus of L minus 1 plus 1 and so on. Index will be increasing here, right? At some point of time you will find Sn and so on and so forth. Okay. So, this will be the data plus it will be some vector will be there. What will be the channel matrix n? This will be the case HL minus. It is a plain simple application of linear algebra. Whatever you can write it here, whatever is shown here, the same thing you can see it here. Okay. Then it will be HL minus 2, H1, H0, 0, 0. It's like a shifted, like a Toeplitz matrix. That is what we are saying it, right. Then next will be again double 0, and finally at the end you will be having at some point of time HL minus 1, and this all will be zeros. This is something like that, right. Now, this kind of form is very popular for all our communication system. This is a system of linear equation. Just think about it. What am I getting? Left side I have a observed vector, right side I have bunch of matrix and vectors. So, can I write this whole thing as y bar is equal to some equivalent matrix called H. What is that H? In this particular case, this whole this whole matrix, and it is a Toeplitz matrix, right. As you can see, it is a right shifted. You can form one row and then it is getting right shifted. Okay. So, now can I think of it some sort of a system of linear equation? Yes, this is what is coming, S bar plus V. This is the system of linear equation. What is S bar? This S vector, that is your data. So, that is nothing but this vector. So, it starts from here and ends here. So, what is the dimension of it? N plus L. So, you have L data extra and then you have Nx. So, this will be N plus L cross 1. That many number of data is present. Okay. And accordingly, see if this you have N here. So, this will be N cross 1 dimension and this will be adjusted accordingly, N cross N plus L and so on and so forth. So, that dimension will adjusted accordingly. So, this is the key part. So, that means this is the start point for our signal processing. This should be very clear. So, this is how I can create, and this signal processing this equation is so important. It gives rise to most of our analysis, most of our detection estimation algorithm, everything comes from this system of linear equation. Okay. So, this equation can be somehow formed, and this is, you can think of, though it is a matrix vector involved, but whole thing I am just making it using single antenna. So, here what is what my key point here? I am observing multiple data at my time. So, I can do something in the time, I can do something in the space, I can do something in the frequency, but this is a simple observation where where I am observing the data at different instances of ADC and trying to create some sort of a system of linear equation. Now, once I am given this kind of equation, I create ONDAR out of it. Okay. So, next class I will talk about how our data can be extracted, how exactly a channel can be estimated, and after that we will move to millimeter wave. So, this is the fundamental equation that, or a signal processing, first part of my signal processing in a communication system. Okay. So, this is the reference. Thank you.